So today it's my last lecture. So I just want to make some concluding remarks just about the moments of the measure, and then I want to have just a formal discussion about possible applications. So to conclude my lecture, just a few remarks about the moments. Maybe it's number 4. I don't remember. The number is random. Okay. Moments. So why is it interesting to have properties about the moments? Because remember that when you take the chaos, you construct it as the limit of a martingale, and we have seen that it's interesting to study the chaos when your martingale is regular. And a very simple way of ensuring regularity of the martingale is to be bounded in the LP spaces for some given P. So if the martingale is bounded in LP, in LP for P bigger than 1, then it is regular. So, so it is regular, but the limit possesses also moments of order P in that case. So it's interesting to study the question, and in a way, this is results concerning the moments are maybe simpler to prove that than the results of Kahn about the degeneracy, but in practice they are more useful. Okay, so just I want to give you a theorem proved by Kahn. So consider a multiplicative chaos. Computed at the Lebesgue measure. At the Lebesgue measure. And associated to a P as usually. So P of X is just gamma square log plus of T over X plus some nice function G. So we take a gamma square less than 2 times the dimension. So your martingale is this martingale with instead of sigma, I put the Lebesgue measure. So since your gamma square is small enough, your martingale is regular, and you have some properties on the moments. So for each compact set K, you have the expectation of the chaos to the power Q is finite. It is equivalent to having gamma square less than 2 times the dimension over Q. Okay, so well, I won't prove this theorem, but I will just give you some simple explanation. So this is not proof, this is just remarks. Well, in practice, the moments that are easily computed are the integer. for the integer value of n, it is easy to compute to see if it's finite or not. For instance, well, when q is equal to 1, you know that the expectation is just the Lebesgue measure of k. When q is equal to 2, you can make a formal computation that is true actually. So your chaos is just formally this quantity. And then you write your square as a double integral. So you see that you have to compute something like that. Plus xy. So when I compute the expectation here, for x or for y it is the same thing. So I just write this expectation. Okay, so I just write this as a double integral, and I can switch. I can put the expectation inside, and then you just have to compute the Laplace transform of a Gaussian random variable. Okay, so you just have something like that. If you do your computation, you obtain this relation, where P is the kernel, and this should give you something like that. The only interesting part is the log, because G is bounded. So you just have to see if this integral is finite. So P is more or less a log. So you have gy. So if you make sure that this integral is finite, you have a moment of order 2. Okay? So for instance, you have to assume that gamma square is less than just have to, in dimension 1, you just have to assume that the gamma square is less than 1. Okay? So this is in practice. This is the only thing you have to compute, because in turbulence, in finance, the gamma square is very small. So the gamma square in practice is always very small. So this inequality is always satisfied. So you have a moment of order 2 with no difficulty. Okay, in dimension G, just put a G here. Okay. So and what is not very difficult to see is that this condition implies this one. Okay, I will show you that this is true. So if this is true for every compact set, so I do the proof in dimension 1. If this is true for every compact set, in particular, I have q lambda of the segment 0, 1 to the power q is finite. Okay? And this quantity, I can rewrite it as a sum. So this is just the sum. Yes. I take q bigger than 1. Okay, sorry. Now I use for a q bigger than 1, I use the fact that this function is super additive. Okay, so this should be bigger than the sum of the q's power of the corresponding term. Okay, and actually all the proofs that appear here are just about subadditivity or superadditivity. Okay, so this is just a simple proof, but this illustrates the whole proof. So this is bigger than the sum of the expectation of each term to the power q. So now by stationarity, I can replace my k by 0. Okay. So each term here has the same value by stationarity. So this is just n times the expectation of the segment for k is equal to 0. So 1 over n. Are you okay with that? Okay. So now what I use here is the power law spectrum. I know that this quantity should behave like so when the n becomes large, this quantity is just 1 over n to the power the structure function. That is what we saw yesterday, times eventually a constant. Okay. So you have something that is finite and fixed. That should be bigger than this quantity for all n. So this gives you that n minus cq should be less than 0. Okay. And so this gives you the condition C of q bigger than 1. And I gave you yesterday the expression of psi of q. And if you do a simplification, you will find gamma square less or equal to 2 over q in dimension 1. Okay. So my inequality is not optimal, and if you want to have the strict inequality, you have to be you have to work a little more at this step when I use the superadditivity, but this is just an improved superadditivity relation. So this is around the same computation. So this is just about the moments, and this is the end of my lecture. Now I just wanted to give you some application, and maybe if you have questions about modelization or application, we can discuss about that. Well, there are two kinds of applications that I want to talk about. There are some applications about finance, turbulence, and there are very strong similarities, so I want to do the comparison as much as I can do it. So in finance, you have Well, this is what I want to talk about is the Mandelbrot model. So, well, when you observe the log price, so xt is the price of an asset. Stock or index. Well, maybe it's not the good terminology. Index are SP 500 or Nasdaq or some kind of such stuff. So when you look at an index, you should observe for the log. The log of xt should satisfy some empirical properties. So you should have no, this is empirical. You should have the stationarity of the increments. So the stationarity, it's not always true. It's more or less true. It depends on the period you consider. Okay. Well, for instance, in my introduction, I have plotted the page 4. I have plotted the Nasdaq, the increments of the Nasdaq, and the SP 500. Well, so you have data for this kind of things, and well, the period is very long. It's from 2001 to October 2009. So for this whole period, you may approximately observe that the increments are stationary. Okay. What is obvious from the picture is that they should be centered. Okay. They are more or less centered at 0. They should be centered. You may, what you want to have is that they are decorrelated. So so you should have a, let us call this yg. You should have the expectation of yg s plus g minus is equal to 0. That is necessary. Why? Because if this is not equal to 0, when you are at some given date t, if you have correlation, you can make money after your date. Okay, because you know how it will evolve. Okay, so this should be true, and this is true. But you should have a long-range correlation. So for the Black-Scholes model, this is true, and this is true. You should have correlations, long-range correlations. That is what I tried to explain yesterday. As soon as you have a strong activity of your stock, in the coming days you should observe also a strong activity, because this is correlated. Okay, and you can observe the correlation on page 5. I've plotted the Nasdaq or SP 500, and there are the data, and there is some kind of fit. I tried to fit with a curve that is approximatively a log. Okay, so you see that it more or less fits the curve, except it may be at 0. Okay, it's very noisy for the value. When you compute the correlation, when S is very small, it's very noisy when you observe your data. So the exact value at 0 is difficult to compute. Okay, so but you can approximatively fit your curve with a log function. So long-range correlation. This means that the expectation of sorry, not the expectation, the correlation, covariance of YG so well, this is difficult to know what you put in the power of mu, but well, what is sure is that mu is very small, and if you take some kind of limit when mu goes to 0, this is kind of a log. When mu goes to 0, you can approximate it by a log. Okay, this is not bad. Sorry. You can choose whatever you want. So, well, and this is not true for the Black-Scholes model, because you know that for the Black-Scholes model, the correlations are equal to 0. Okay. When you took the increments of the Brownian motion, you should have 0. Okay. Sorry? Yes. This is YG. Thank you. Well, and when you have the log price, well, the financial guys usually define the quadratic variation. So this is the how do you call it? Quadratic variation. You must be able to define the quadratic variation of your process Y. This is called the volatility process. Volatility process. You should be able to define such a process because numerically and empirically, when you observe data, this is more or less finite. So you must be able to define such a stuff. And why do I say that? Because there are guys that use Levy processes to. So they say, well, the Black-Scholes model is not good because the Brownian motion does not satisfy many properties that are expected here. In particularly this one. Okay, and there are other things like maybe it's important to write. I do not write here. Just yes. The third and fourth because I forgot to put quadratic variation. Okay, and okay, you are right. Okay. So this is the quadratic variation between the time t and t plus s. You are right. Yes, and the last thing. So it is just above the red line. This is fat tail distribution. Functions of yg. Okay? So, for the Black-Scholes model, obviously, the two last conditions are not true. Okay? So, there are guys that use Levy processes to enlarge the tail distribution. Okay? But the problem is that you cannot define your volatile process as soon as you have a fat tail distribution with Levy processes. Yes. So there is a contradiction here. You have to make both conditions valid. Okay. And furthermore, with Levy processes, this is always equal to 0 because the increments are independent. So there are some kind of contradiction with the use of Levy processes instead of a Brownian motion. So what is the idea of Mandelbrot? So the model is the following. Well, say log of xt is equal to a Brownian motion. So this is not good. But instead of seeing it at a deterministic time, you compute it at a multifractal time. So m, well, to make this simpler, I just put mt. Mt is just the Gaussian multiplicative chaos computed at a segment. Here, okay. This gives you an increasing process, so that you can change the time of your Brownian motion. And well, to fit your data, you can put a fixed parameter here, okay, to change the size of. Well, and now you see that well, your process here, you can prove that it is continuous. Okay, so we haven't seen that, but this is continuous. So the quadratic variations are well defined, and the quadratic variations are just given by so there should be sigma, and here you compute the variation. This gives you mt. Okay. So, so this is good.
So you assume that the time mt is independent of
Yes, yes. The time, yes. This is independent. So m independent of b. This is a good question because this is the last point of my discussion. Okay, and yes, I don't have to forget. Okay. Yeah. Okay. So, well, the advantage of well, we haven't discussed that point, but when you look at something that is multifractal, you should have a fat tail distribution. So this is good also. Okay. Now you can well. You change well, you change your time, but if you do a straightforward computation, you see that for this model, the increments are decorrelated. So when you compute that, you just condition by m. You observe that for your Brownian motion, this is 0, and you suppress the conditioning, and this is 0. Okay. Well, stationarity, it is also obvious because your measure is stationary, and B has stationary increments. It is centered. This is also obvious. So maybe the only point you have to check is this one. Okay. So well, I just give you that. Well, actually, for the Mandelbrot model, you find. You can try to do the computation if you want. Sorry. Gamma square. Okay. So you find a power decrease, and well, this is as I told you yesterday. Your parameter, your gamma square is very small. It's approximatively gamma square in finance is should be around 2 or 3. Let us say 3. Okay, well, it's not important, but this is very small. So you have very long correlation. Okay, this well, actually there is a guy. His name is Musi. You told me about him yesterday, and he told me that he tried to find the correlation length in finance. He said that he managed to collect data for 80 years, and he continues to find correlations. So. Yes. You have to check stationary, but approximatively you can find correlations. So. Yes. Well, the question is, well, there is a last point here that I have not. So the Mandelbrot's model is not that bad because it fits all these points here. But there is a last point that is not satisfied, and it is a good toy model for turbulence. So before talking about the last point, I will talk just a bit about turbulence. So well. Well, when you study the motion of a fluid, usually you look at the Navier-Stokes equation. Well, it's given by g over dtu plus u scalar the gradient of u. This should be equal to minus the gradient of the pressure. Sorry. Plus some dissipative forces plus external forces. Okay, this is the Navier-Stokes equation, and it is important that you consider the 3D case. Otherwise, this is more or less simple in comparison with the 3D case. Okay, well, what is difficult is to add the incompressibility condition. As soon as you assume as soon as you assume that your fluid is incompressible, this is very difficult, and I don't know anything about the solution. Okay, this is a very big, very challenging problem. So, physicists, well, finding the solution is very difficult. So, Kolmogorov said, okay, we can tackle the problem statistically. So, what he said, he looked at the Navier-Stokes equation, at empirical facts, and he said, well, I can develop a theory, and more or less, you should have some properties. Well, this is called the K62 theory. There is a theory before, but I don't talk about it. Well, the unknown here are U and P. This is an equation about U and P. You have to find simultaneously the pressure and the velocity of the fluid. This is the velocity. Okay, so the velocity field is a function from R3 into S3. Well, Kolmogorov said that when the velocity of the fluid is very large, or meaning mu here is very small, you should have a stationarity of the fluid. You should recover some statistical property. Statistically, sorry, you should be stationary, you should be isotrope. And well, he said that you should have a power law spectrum, more or less. The expectation of so this is a fixed real number, so L is positive. E is just a unit vector. So this is the connection with multifractality. And why did you assume that? Because they observe in turbulence that there is intermittency. Okay, so this is a rough description, but this is not enough, and there is a.
I'm sorry. And when you write the expectation, should you understand?
Yes.
And saying statistically with respect to what?
So. Yes. So when you just a few remarks before answering the question. So this is a function of t and x. So there is no t inside. So first you suppress time because you assume that you are in a steady state. Okay. So you suppress time. Then you say, well, you see your velocity field as a random variable, and you can do many. Well, this is just. There is no rigorous fact behind that. Just you observe your field, you observe that is very irregular, and you say, well, I just do as if it is a random variable, and I do many experiments, and I observe that in my experiments, this is
So we should think of this as many experiments rather than taking the expectation.
yes, you do many experiments, you take the expectation, and you observe that you have such behavior. Okay. But this is maybe a rough description, but this is GIG. Okay. So this is for intermittency, and well, here you observe that you have a 3D field, and so we don't know how to construct 3D multifractal fields that satisfy some good properties. That's why instead of looking at the field, we look at the local energy dissipation. That is usually denoted by epsilon. And this is just a random measure that measures the energy dissipated by the fluid in a domain. You look. You have your experimentation cell. You look at a domain G inside your cell of experimentation, and you compute the energy you observe, the energy dissipated by the fluid, and well, this gives you a quantity. So this is a function from the. This is a random variable taking values in R, and this is called the local energy dissipation. Why do I study such an object? Because now I take value in R.
What's the definition? So this is just a kinetic energy?
No, the definition. You can express your dissipation with the velocity field, and the expression is well, up to normalizing constants. So your expression is just mu over 2 integral over a. So you take dy plus square dx. Okay. So and
physical doesn't just mean that we have the viscosity and so then it's just
you have this.
Viscosity term.
Ah yes.
Then energy dissipates.
Yeah. Yes. There is well.
Like density of this process.
Well, I'm not a physicist, but there is some kind of competition between the energy you put inside the fluid here, and there are some scales when you look at the fluid where intermittency is observed, and at very small scales you should observe the energy of the fluids dissipate, and well, I don't know what happens at the very small scales. When you observe intermittency, it's at intermediate scales, and my modelization is just for intermediate scales. Okay. Well, we work with a physicist of turbulence, and he says that the modelization at very small scales is very difficult and open. They don't know what happens exactly. So this is just a rough description, of course. What do I want to say? Yes, the viscosity forces are very small. Okay, so here you may think that when mu here goes to 0, you may have this quantity that is equal to 0, okay? But you can prove just with the Navier-Stokes equation that when you take the limit here, when mu goes to 0, this is not 0. Okay, just you can prove it rigorously from the Navier-Stokes equation. This is a paper of Raoul Robert. I don't remember the name of the paper, but he proved that rigorously. So, so this tells you that you may look at this quantity in turbulence because it has some interest because of this limit. Okay. So now the original idea of Mandelbrot was to modelize. Kolmogorov and Obukov gave the description of what a good model for energy dissipation should be, and Mandelbrot and then Kahn for mathematicians constructed the multiplicative chaos. Why chaos? Why? Because they want to have such a property here. Okay. So this is the main motivation for the construction of multiplicative chaos. But so this is more or less the local energy dissipation is more or less well understood now mathematically and physically. But there is the problem of modelizing the velocity field. And when you look at the velocity field, there is some additional property that should be satisfied. It is called the 4/5 law of Kolmogorov. So when you give a model for turbulence, if this law is not satisfied, there is nobody that will listen to you. Okay, so. What is 4/5? Well, yes, I will try to state it. So this is some kind of the idea behind the 4/5 law of Kolmogorov is that there is some strong dissymmetry in the field. Okay, so what is it? It should be something like that. You take this quantity, because here I forgot to put the absolute value. You take a scalar product and you take the absolute value. So this is not this is a positive quantity. When you take the same quantity, you don't put any absolute value here. So should be something like minus 4/5, say. And I multiply by a constant because I surely make a mistake. Okay. So, but what is important is that here you should when if your fluid is smooth, you should have L to the power 3 here. So you take the power 3 of something that that has length L, and you get an L to the power 1. What is behind the exponent here is intermittency. But if your fluid is symmetric, this quantity should be 0. Okay. Just think to get simple. Think of the powers, the third moment of a Brownian motion. You take the expectation and you get 0. Okay. Because the Brownian motion is symmetric. Here you have a strictly this is a strictly positive quantity. So there is some strong dissymmetry in the fluid. Okay. So this is something that we cannot get with our model. Okay. And why is it interesting in finance? Because in finance, you get rid of the problem of the dimension, and there is something called the leverage effect. This is some kind of dissymmetry in the evolution of your stock. So you observe in finance that the expectation of sorry, log xt. Well, you look at something like that. You look at the expectation between the quadratic variation between the time t and t plus s and the return, and you observe something that is very close to the 4/5 law Kolmogorov. You observe something like a function of s, and this is not 0. And for the Mandelbrot model, as I wrote it, this is 0, and so you have to explain in finance where dissymmetry comes from, and actually you can do some stuff by correlating the Brownian motion with your change of time. That's your question. So there are some solutions that can be that allows you to understand the 4/5 law of Kolmogorov, but in finance. So you take the same model, you take log xt is equal to b mt, but there are some correlation. So you can construct good processes by correlating. So we are trying to do the same thing in turbulence. And but we don't manage to do anything. This is good. We have to work, but so and my last point will be to talk about the modelization. What we are working on is the following stuff. Well, there is a a physicist that that made some kind of Taylor expansion of the fluid around zero, and he finds that yes, in time he starts with an initial condition, and he do a Taylor expansion at zero, and he finds that the velocity fluid should be approximatively given by a chaos. So well, minus c of x. Gx. Well, this is approximatively something like that. This is not true. Sorry. Yes. He finds that here you put a white noise. So this is a white noise. Three-dimensional. This is just a 3D white noise, and here you have a Gaussian process, but taking values in the set of matrices, of 3D matrices. Okay, so X takes values in is defined on R3 and takes values in the set of matrices, three-dimensional matrices. So this field is a Gaussian process. He finds that empirically you can observe that the entries of your matrix here are correlated, but independent from the off-diagonal terms. Okay, so you have to define a theory of multiplicative chaos with respect to matrices. And the difficulty here is that when you look at Gaussian random matrices, you don't have any commutativity property. Okay, so when you want,
C?
Sorry.
What is C?
Yes, C is just your renormalization. First, I want it's tantalizing to write that. Okay, and it's not far from that. Okay. Well, you have to define the chaos with respect to matrices, but for the theory to be simple, you need some commutativity property. But here, when you look at Gaussian random matrices, there is no commutativity property, excepted maybe statistically. Okay, when you take, for instance, if your random matrix is not so bad, it should be isotrope, and for good expectation of matrices, you can recover some commutativity property, but just in expectation. Okay, so this is an open question, and we are working on that stuff now. Okay, this is just what I want to explain. I've finished.
What's A here?
Sorry.
A, the integration.
Yeah, sorry. This is yes. Let us say the integration variable is y, and let us say that you just translate a set. Okay.
And what's the set?
Anything you want. Just a set. Let us say an open set. Open set. Okay. How can this depend on
the result of the integration?
Yes, you want to compute u of x, so you have to make the dependence with respect to x somewhere. It's just as if you take when you want to construct a stationary process. For instance, you take a random measure mu, and you integrate something like that. Okay, this is the simplest way of constructing something stationary, and this is the same kind of thing. Instead, I just here f as the indicator function of a set. Okay. So here you get something stationary because when you translate the difference between the random here, this is a random measure. So you compute your measure at a set, but here you want to have a field. So you have to make an x appear somewhere. Okay.
And where is time?
Where is the time? Yeah, there is no time because I am in a steady state. So I suppress the time dependency. We look at turbulence in a steady state. I am stationary in time, so but you can try to modelize something with time here. And if you look at the properties of your field with respect to time, you will also observe intermittency. There are some similar phenomena with respect to time. But if you, at the beginning, if you start to understand without time, it's not bad.
Just don't get it. That's a number, yeah? Well,
This is in R3.
yes. So you're saying that it satisfies the NS equation?
I'm just trying to modelize.
What's the meaning of this integral?
Sorry?
What's the meaning of this integral? Is this a sort of solution or what?
No. Yes, this is just a statistical solution, and
A statistical solution?
well, either you try to solve this equation, and we don't manage to do that. What we can, what we do is the following: we observe many empirical facts, and we say, well, we are trying to construct an object that reproduces all your phenomena, your statistical observation. Okay, and more or less it should be close to this expression.
This is not a random variable, is it?
This is not a.
This is not a random vector, is it?
Yes, here you have a three-dimensional matrix. Yes, so the exponential is a matrix 3, 3. You integrate with respect to W, that is a vector, 3. So you get a three-dimensional vector.
So in what sense does it? You mean that it reproduces the correlation factor, the moments?
Yes, you have the moments, you have the 4/5 law, you have numerically you have the 4/5 law because we don't know how to prove that this guy satisfies the 4/5 law. We have some special properties of the eigenvalues of the field, but this is we have all the properties we want to have, but we don't know how to prove anything. So this is just some numerical experimentation. And we are now trying to prove something.